Picture this. NASCAR 1969. Smoky Unix car blows through tech inspection. Officials find nothing wrong. The engine looks completely stock. Then it wins by 2 laps. When they tear it down again, every single component is technically legal. But the valve angles are off by half a degree. The ports are polished to a mirror finish you can't see without a microscope. The pistons weigh 30 grams less than factory. Welcome to the dark art of invisible horsepower. Modifications so subtle, so cleverly disguised, that NASCAR spent decades trying to ban them and failed. These aren't your obvious cheats like nitrous bottles or oversized engines. These are engineering masterpieces that lived in the shadows, exploiting the gap between the letter of the law and the spirit of competition. Let me take you inside the most brilliant game of cat and mouse in motorsports history. 10 engine modifications that made NASCAR officials lose sleep, rewrite the rulebook, and still couldn't catch them all. We're talking about an era when stock car actually meant something. The late 1960s through the 1990s. NASCAR wanted these cars to represent what rolled off the showroom floor. The manufacturers wanted to win on Sunday, sell on Monday, and caught in the middle were the most creative engineers in racing, men who could find 20 horsepower in a valve spring and hide it from the best inspectors in the business. The stakes? Millions in prize money, factory backing worth tens of millions more, and the kind of bragging rights that sold cars for decades. Ford versus Chevy versus Chrysler, with each camp employing engineers who thought like safecrackers. Every new rule was just another lock to pick. Number 1, trick valve angle machining. This one drove NASCAR absolutely insane for 15 years. Here's what teams figured out. If you alter the valve angle by just half a degree, we're talking about a change so subtle you need precision measuring equipment to detect it, you can dramatically improve airflow into the cylinder. The stock small block Chevy ran 23-degree valve angles. Teams would machine the heads to 22.5 degrees. That half-degree difference meant the valve opened into a slightly better flow path. At 7,000 RPM, that translated to about 15 extra horsepower. The genius part? The heads still looked completely stock. You could put them next to a factory head, and unless you had a degree wheel and knew exactly where to measure, you'd never spot the difference. NASCAR tried to ban it in 1971. Teams just got better at hiding it. They'd machine the seats at different angles to compensate visually. They'd modify the valve guides to maintain stock appearance. Some teams even made special inspection heads that were truly stock, then swapped them after tech. By 1985, NASCAR was using computerized measuring systems. Teams responded by altering only the exhaust valves, which were harder to check. The inspectors would catch one team, issue a memo, and 3 weeks. Later, 5 teams would have a new variation. This went on until the late 1990s when NASCAR finally mandated specific cylinder heads. Even then, teams found ways to massage the rules. Number 2. Micro-polished intake ports. This is where science met art. A stock intake port has a slightly rough surface from the casting process. That texture creates boundary layer turbulence that restricts airflow. Teams discovered that if you polished these ports to a mirror finish, and I mean mirror, like 0.5 micron surface roughness, you could gain 20 to 30 horsepower on a restrictor plate engine. But here's the catch. You can't see this polish without magnification. To the naked eye, a professionally polished port looks almost identical to a cleaned-up factory port. NASCAR inspectors would run their fingers through the ports, but skilled porters learned to polish only the critical areas, the short side radius, the bowl area behind the valve, the roof of the port. Leave the rest slightly rough, and inspectors felt nothing unusual. The really clever teams took it further. They'd polish the ports, then chemically etch them to create a specific texture that was still smoother than stock, but felt rough to the touch. Richard Childress Racing got caught with this in 1995. Their penalty? A slap on the wrist because NASCAR couldn't define exactly how smooth was too smooth. They tried to implement surface roughness standards. Teams just moved the polish to areas inspectors couldn't easily reach. Number 3 brings us to hidden lightweight pistons. This is engineering at its absolute finest. A stock 350 Chevy piston weighs about 550 grams. Racing teams figured out how to make pistons that looked identical but weighed 450 grams. That's 100 grams of reciprocating mass gone from each cylinder. Multiply by 8 cylinders, and you've reduced reciprocating weight by almost 2 pounds. Why does this matter? Less reciprocating mass means the engine revs faster, pulls harder out of corners, and puts less stress on the connecting rods. We're talking about pistons forged from 26-18 aluminum alloy instead of the standard 40-32. Thinner ringlands, 0.043 inches instead of 0.060. Hollow piston pins made from tool steel. Box beam structures inside the piston that you couldn't see without cutting it apart. NASCAR would weigh pistons during inspection. So teams got creative. They'd make the pistons the correct weight, but remove material from places that didn't show. Underneath the crown, inside the pin bosses, behind the ringlands. Some teams even experimented with ceramic coatings that looked like aluminum but weighed less. When NASCAR started cutting pistons apart, teams made the visible sections normal thickness and hollowed out the centers. The ultimate trick? Varied wall thickness. Make the piston look stock from any angle you'd cut it, but use computer modeling to remove material from low-stress areas. NASCAR tried to mandate minimum thicknesses in 1987, 1991, and 1994. Each time, teams found new ways to interpret the rules. It wasn't until spec pistons became mandatory that this arms race finally ended. Let me tell you about number 4, Undercover high-rate valve springs. Valve springs determine how high an engine can rev before valve float occurs. Stock springs were rated for about 6,500 RPM. Racing springs could handle 9,000 RPM, but they looked identical from the outside. The secret was in the metallurgy and the winding. Teams used exotic alloys like chrome silicon or even titanium wire. They'd use progressive rate springs that looked linear. They'd nest multiple springs inside each other, a practice called dual or triple springs, but machine the retainers to hide the extra springs from view. Some teams even developed springs with hollow wire, same outside diameter, less mass, higher RPM capability. NASCAR would test spring pressure on the bench, so teams developed springs that showed correct pressure at inspection height but had much higher rates at full lift. They'd shot peen the springs to increase strength without changing appearance. They'd use cryogenic treatment to alter the grain structure. One team, I won't say which one, but they won a lot in the 1980s, developed a spring that would lose pressure when cold, but gain it back when hot. It passed tech inspection every time. The inspectors tried everything: spring rate testers, durometers to check hardness, even X-ray machines. But for every test NASCAR developed, teams found a workaround. This cat-and-mouse game continued until NASCAR mandated spec valve springs from approved manufacturers. Even then, teams would massage the springs, breaking them in on special machines that would increase their rate without leaving visible evidence. Number 5, stealth compression bumps. This one's beautiful in its simplicity. Compression ratio is power. Every point of compression is worth about 3% more horsepower. Stock engines ran about 9.1 compression. Teams wanted 12.1 or even 13.1. But how do you hide 3 full points of compression? You do it in tiny increments spread across multiple components. Mill 0.005 inches off the deck surface. That's 5/1000ths, thinner than a human hair. It's virtually impossible to detect without precision measurement and raises compression by 0.2 points. Take another 0.010 off the head surface, another 0.3 points. Use a thinner head gasket that compresses more when torqued, 0.2 points. Pistons with slightly taller crowns, 0.4 points. Longer connecting rods that push the piston higher, 0.3 points. None of these changes are visible to the naked eye. Even with measuring tools, you'd need to know exactly where to measure and what the original specifications were. Teams would alter blueprint specifications to show their illegal dimensions as stock. They'd create elaborate paper trails showing their engines were legal. Some teams even made special inspection engines with stock compression that they'd swap for tech inspection. NASCAR tried to combat this with Whistler tests, measuring cylinder volume with the piston at top dead center. Teams responded by offsetting the changes: lower compression on intake valves, higher on exhaust; normal compression at TDC, higher compression at ignition timing. They'd even use asymmetric combustion chambers that looked stock from the spark plug hole but had less volume overall. Number 6 takes us into the realm of covert oil pan modifications. This sounds boring until you understand what it meant. A stock oil pan holds oil. A modified racing oil pan is a power-adding component that can be worth 20 horsepower and prevent engine failure in high-G corners. Teams developed oil pans with hidden baffles and trap doors that kept oil around the pickup during hard cornering. They'd use scrapers and windage trays that stripped oil off the crank, reducing parasitic drag. Some pans had false floors that looked stock from outside, but created a second sump for better oil control. The really clever ones had internal crank scrapers that were invisible unless you cut the pan apart. The 1984 Daytona 500 winner, I can't prove it but everyone knew, had an oil pan with hidden channels that directed oil away from the crank while appearing completely stock. It had internal baffling that looked like normal pan reinforcement ribs. The drain plug was even in the stock location, but internally the oil flow was completely different. NASCAR inspectors would check oil capacity, so teams made pans that held the correct amount but distributed it differently. They'd check external dimensions, so teams kept those stock but changed everything inside. They'd even weigh pans, so teams used thinner steel with more baffling that weighed the same. By the time NASCAR figured out one trick, teams had moved on to 3 new ones. Number 7, secret crank knife edging. The crankshaft is the heart of the engine, converting linear piston motion into rotational force. A stock crank has fairly blunt edges on the counterweights. Teams discovered that by knife edging these counterweights, grinding them to sharp edges, they could reduce windage losses by up to 15 horsepower at high RPM. But here's where it gets clever. The crank still weighs the same. The stroke is identical. The journal sizes are stock. Unless you knew exactly what to look for, a knife-edged crank looked like a well-balanced stock unit. Teams would only knife-edge the leading edges, leaving the trailing edges stock. They'd polish the journals to reduce friction, but leave the counterweights rough to hide the modifications. Some teams went even further. They'd gun drill the main journals, drilling tiny holes through the center to reduce rotating mass without changing external dimensions. They'd use tungsten plugs in the counterweights to maintain stock weight while removing steel elsewhere. They'd even experiment with offset grinding, where the rod journals were moved slightly to increase stroke without changing the main journal locations. NASCAR tried to police this with dimensional checks, weight checks, even hardness testing. But a properly modified crank passed every test. It wasn't until they started using coordinate measuring machines in the 2000s that they could reliably detect these modifications. Even then, smart teams found ways to modify cranks that CMMs couldn't detect. The 8th modification showcases pure metallurgical genius, exotic alloy connecting rods. Stock rods were forged steel, weighing about 650 grams each. Racing teams developed rods that looked identical but weighed 550 grams and were twice as strong. They used materials like 300M steel, Airmet 100, even titanium when they could get away with it. The beauty was in the deception. They'd coat titanium rods with a ferrous spray that made them magnetic like steel. They'd use steel big-end caps with titanium beams. They'd even make hollow rods filled with oil that weighed the same as solid steel but had better strength-to-weight ratios. One team, allegedly Junior Johnson's, made rods from miraging steel that looked and weighed exactly like stock rods but could handle 10,000 RPM. When NASCAR started checking rods with magnets, teams switched to magnetic stainless alloys. When they started weighing them, teams made them the correct weight, but stronger. When they started hardness testing, teams heat-treated the surfaces differently than the cores. The famous helicopter rod scandal of 1988 involved connecting rods made from the same aluminum alloy used in military helicopters, coated to look like steel. Number 9 brings us to flexible intake gaskets. This is so simple, it's genius. The gasket between the intake manifold and cylinder head is supposed to be just a seal. Teams realized they could use this gasket as a spacer to increase plenum volume and port length, worth 10 to 15 horsepower. They'd make gaskets from materials that compressed during installation but expanded when heated. The gasket would pass tech inspection at 0.060 inches thick but expand to 0.100 inches at operating temperature. They'd use laminated gaskets with hidden spacers between the layers. Some teams even made gaskets with built-in venturi effects that increased airflow velocity. The really clever part? These looked exactly like stock gaskets, same color, same material appearance, even the same part numbers stamped on them. NASCAR would check gasket thickness, so teams made them compressible. They'd check material, so teams used approved materials with hidden cores. They'd even check installed height, so teams developed gaskets that only expanded after multiple heat cycles. Finally, number 10, ultra-thin low-drag piston rings. This modification was so effective that NASCAR still struggles with it today. Stock rings are about 1.5 mm thick. Racing teams developed rings as thin as 0.7 mm. Thinner rings mean less friction, less blow-by, and more horsepower, up to 20 HP on a well-developed engine. But these weren't just thin rings. They used exotic materials like ductile iron with molybdenum facing. They had special coatings like chromium nitride or diamond-like carbon. They used gas-ported designs that looked solid but had tiny holes that used combustion pressure to improve sealing. Some teams even developed rings that would wear into a specific shape that reduced friction while maintaining seal. NASCAR tried to mandate minimum ring thickness. Teams made rings that measured correctly but had relieved backs. They tried to specify materials. Teams found new coatings that weren't specifically banned. They tried to check ring tension. Teams developed rings that had low tension until they heated up. This battle went on for decades. Here's what made these modifications truly brilliant. None of them alone would win a race. But stack them together, trick valve angles adding 15 horsepower, polished ports adding 20, lightweight pistons adding better acceleration, high-rate springs allowing 500 more RPM, a point of hidden compression adding 3%, better oil control preventing power loss, a knife-edged crank reducing drag, stronger rods allowing higher RPM, intake gaskets adding volume, and low-friction rings reducing parasitic loss. Suddenly you've got 50 to 70 horsepower that nobody can find. The teams that won consistently weren't the ones with one big trick. They were the ones that perfected a dozen little tricks that inspectors couldn't detect. They understood that racing isn't just about going fast. It's about going fast within the rules, or at least appearing to. What fascinates me most about this era is the pure engineering creativity it demanded. These weren't wealthy teams with unlimited budgets and wind tunnels. These were skilled craftsmen with lathes, grinders, and brilliant minds who could see opportunities where others saw limitations. They turned rule enforcement into an engineering challenge and made NASCAR inspection a constantly evolving battle of wits. The legacy of these modifications lives on today. Modern NASCAR uses spec engines with sealed components precisely because of these innovations. Every tamper-proof seal, every mandatory part number, every technical inspection procedure exists because somebody, somewhere, found a way to make a stock part very much not stock while looking completely legal. Think about the mindset required. You're not just building a fast engine, you're building a fast engine that has to fool experts who know every trick in the book. It's like being a magician whose audience knows how magic works. The level of detail, planning, and execution required is staggering. One former crew chief told me they spent more time figuring out how to hide modifications than developing them in the first place. These modifications represent something uniquely American about our motorsports. It's not enough to be fast. You have to be clever. It's not enough to have the best equipment. You have to outsmart the competition and the officials. It's engineering as gamesmanship, where the real race happens in the garage at 2 a.m. when you're figuring out how to make a valve spring that passes inspection, but revs to the moon. Today's NASCAR is faster, safer, and more competitive than ever. But something was lost when these Wild West days ended. The era when a clever engineer with a die grinder could find speed that million-dollar teams missed. When innovation meant more than just refined simulation. When the difference between legal and illegal was measured in thousandths of an inch, and the skill of the inspector. These 10 modifications aren't just historical curiosities. They're monuments to human ingenuity, proof that wherever there are rules, there will be brilliant minds finding ways to bend them. They remind us that racing has always been as much about intelligence as courage, as much about creativity as speed. The next time you watch a NASCAR race, remember that behind today's spec engines and sealed components lies a history of brilliant deception. Every horsepower was fought for, hidden, discovered, banned, and fought for again. That's the true spirit of stock car racing. Not just going fast, but finding ways to go faster than anyone thinks possible. What's the most clever racing modification you've ever heard about? Drop it in the comments. If you enjoyed this deep dive into NASCAR's engineering underground, hit that subscribe button for more stories of brilliant machines and the minds that created them. Until next time, keep those engines running. And remember, it's only cheating if you get caught.